Hello and welcome to this webinar on comprehensive design code coverage for pressure vessel and heat exchanger design. Our agenda today will be an overview of AutoPIPE vessel, pressure vessel design code coverage, heat exchanger design code coverage, wind and seismic codes, material standards, local loads, and finally air cooler, storage tanks, and support design codes and standards. AutoPIPE vessel powered by Microprotol is a software that can design virtually any type of pressure vessel, air cooler, heat exchanger, and tanks to most of the major global design codes. One of the strengths is the ability to import thermal design data from HTRI, Aspen, ProSim, and Honeywell, as well as exporting to the major CAD software and plant design softwares like PDS and AutoCAD, SolidWorks, and MicroStation. The software is ideal for both EPC companies as well as equipment design and fabrication companies. There are several advantages of the software, including maximizing productivity of skilled engineering resources, supporting a global market, and improved collaboration across distributed project teams. Many large EPCs, oil and gas owner-operators, manufacturing companies use AutoPIPE vessel for their static equipment design and analysis need. Some of them are mentioned here. After completion of design, the model from AutoPIPE vessel can be exported to MicroStation and AutoCAD for 2D drawing and 3D model generation, as well as creation of 3D model in SolidWorks. AutoPIPE vessel supports several American as well as international codes and standards. This topic will be the central theme of today's webinar. The American codes include ASME Section 8 Division 1 and 2, TEMA Standard for Heat Exchangers Design, API 650 and API 661 for storage tanks and air cooler design respectively, EJMA Standard for expansion joint design. The international codes include French CODAP, British PD 5500, German AD Morgblatter, Russian GOST, European EN 13445, and others, and recently implemented Chinese GB 150 code. Let's look into more details. What are the design codes available for pressure vessel design? The design codes, local load method, flange standard, pipe standard, and bolt types can be specified in the design parameters tab. From the design codes drop-down, the design code is selected. The ASME code available from 1998 through 2017. The 2017 version, which is the latest release of ASME boiler and pressure vessel code, is implemented in the latest released Connect Edition version 6 of AutoPIPE vessel. The availability of previous versions of the design code helps in verifications of calculations of older projects or in case customer specifies an older design code. There are several optional fields other than the design code selection. For example, user may choose to compute MAP, apply code case 2695 rules. Users can also specify the customary or metric units for materials and the material code year. The hydrotest conditions can be specified and UG99C based MAP option can be checked. The external pressure specification section allows consideration of associated shell for inertia calculations. User may choose whether they want to include or exclude trays and stiffeners for external pressure calculations, conical junctions or support lines or not, and minimum space between stiffeners. The code-based default safety factors can be changed to user-defined values for individual load cases. Shown above to the right, the default code-based safety factors used by the software in calculations. The radiography options can be set to full, spot, or none based on UW11 requirements, and weld types set to Type 1 and Type 2. Under Load Conditions tab, the UG23D rule for 20% additional margin for allowable stress for wind earthquake loadings can be applied. There is also a user-defined factor on B stress, which is normally calculated following UG23 rules. This field enables users to input a user-defined value of B stress for external pressure calculations. The MDMT temperature is input by the user, and the software applied the rules of UG20 and UCS66 to find impact test requirements. The PWHT creep and fatigue fields can be enabled by the user. The software issues error messages if PWHT or post-well heat treatment and radiographic testing RT is required. Let's take an example of a vertical column which was designed using AutoPIPE vessel. We select ASME 2017 as design code. In the following several slides, we will consider this example and change the design codes and refer to the design reports to review some of the calculation details. Since the design report is comprehensive and very detailed, we will only look at few sample examples for the various design codes under review. In the external pressure field, the associated shell and stiffeners are enabled for inertia calculations and the conical junctions are considered support lines. We will look at several screenshots of the design report in this and subsequent slides. The hydrostatic test pressures are calculated and listed in the table. Maximum allowable working pressure is calculated. The test pressure accounts for the vertical equipment being tested in horizontal condition by adjusting for the hydrostatic head. The calculations for each component are clearly illustrated in the report with code references and equations. The cylindrical shell calculations shown above with thickness verification and extreme fiber elongation check in accordance with UG 79-1. The external pressure calculations involve evaluation of maximum allowable external pressure and verification that the external pressure applied is acceptable. Internal pressure calculations for conical shell include verification of thicknesses in accordance with UG 32H and Appendix 1-4E. Fiber elongation check performed as per UG 79-1. External pressure check of conical shell performed as per UG 33. Appendix 1-8 rules are applied for the external pressure check on conical shell, the junction inertia calculations performed, and verification of adequate available moment of inertia is performed. The body flange calculations are performed in accordance with Appendix 2. The stresses are computed and checked with allowable stress values and percentage of allowable specified. In the nozzle opening calculations, the nozzle thickness is verified in accordance with Appendix 1-1 and UG 45. The reinforcement checking performed with respect to UG 37, limits of reinforcements verified with UG 40. Further, in nozzle opening calculations, the weld size check is verified with UW 16C and weld load checks performed with UG 41, 45 and UW 15. The MDMT calculations are performed according to UCS 66. The calculations are performed for every component and the rated MDMT of the vessel determined. Now that we have seen an overview of the ASME Section 8 Division 1 calculations, let's perform the design based on Division 2. The checkbox for Division 2 is checked. Note that immediately the program issues a calculation code change warning, drawing attention of the user to the fact that the design code has been changed. Observe in the screenshot at the bottom, the allowable stress values automatically updated to the values of Division 2. This is a very powerful feature of the program as it allows the user to quickly change the code at any point of time in the calculation process, and the program will seamlessly switch and perform the calculations for the reset code when the compute button is pressed. Observe that the RT and weld type fields changes as well. Table 7.2 of Division 2 is now referred instead of UW12. The report design code field is updated to ASME 8 Division 2 2017. The internal pressure calculations for cylindrical shell are performed with thickness verifications as per 4.3.3.1. The code screenshot is shown at the bottom right. The reference of the applicable sections of the design code in the report is very convenient for the user to perform design review. In the external pressure calculations of the shell, the allowable external pressure PA is equal to 47.6 psi is calculated from the predicted buckling stress FIC and is more than the applied external pressure P is equal to 15 psi, so the design passes. The conical shell internal pressure calculation includes thickness verification as per 4.3.4.1. In external pressure calculations for conical shell, the external allowable pressure is calculated like the internal shell as per 4.4.5 and 4.4.6. The allowable pressure calculated to be 165.2 psi is more than the applied external pressure of 15 psi, so the design passes. The large end conical junction knuckle design as per 4.3.12.2 passes as the longitudinal and circumferential stresses sigma sm and sigma theta m are within the allowable values. Observe that the acceptance criteria is clearly specified, enabling a convenient review and verification of the design calculations. In the small end conical junction calculations, observe that since the small knuckle flare radius to thickness ratio is not maintained, it is highlighted in red as it is beyond the scope of applicability of Part 4, which is designed by rules. Code requires application of Part 5 or design by analysis for the same. The nozzle neck required thickness is verified as per 4.5.2 and the opening is checked for adequate reinforcing. Weld check is also performed. The weld size check verified with table 4.2.10. MDMT calculations are performed as per Part 3.11 Material Toughness Requirement. The rated MDMT is evaluated at the end of the calculations. Let's look at the French code CODAP. The versions of CODAP maintained are from 1998 through 2015 revision 10/16. Observe in the screen capture to the right, the options for gas and steam pressure is now enabled so that users can specify. This is a requirement as per French regulation. There is a checkbox to apply PED or Pressure Equipment Directive. The program calculates the test pressure in accordance with the European Pressure Equipment Directive if this field is checked. Observe that the Hydrotest Conditions section offers the user to specify if the vertical vessel is hydrostatic tested in horizontal condition. The report takes this into consideration by applying an additional hydrostatic head as shown in the report screenshot at bottom right. The CODAP hydrotest pressure as shown above on top right is maximum value of 1.43 times design pressure or 1.25 times the product of design pressure and ratio of the material allowable stresses at room temperature to normal operating conditions. The internal pressure calculations of the cylindrical shell is performed as per C2.1.2.1. The table compares the minimum required thickness to the nominal thickness for various load conditions to confirm design sufficiency. The external pressure calculations in CODAP are similar to that of ASME, which involves referring to vacuum curves. The vacuum curve referred in this case is C4-2. For the check thickness of 0.2165 inch, the maximum allowable pressure PA is calculated to be 90.606 psi, which is more than the applied external pressure P is equal to 14.982 psi, hence the design passes. Additionally, the straight section of the conical shell is verified with C4.2.4. The external pressure check involves checking the moments of inertia of large and small end junctions of the conical shell. The inertia calculations are performed as per C4.2.7.6. The moment of inertia contribution from each component, namely the stiffener, cylindrical shell, conical shell, knuckle radius, and the combined section is calculated separately and presented. The stiffener calculations are separately performed as per C4.2.5 and inertia verifications performed. The body flange calculations in CODAP are similarly presented as in ASME Appendix 2. Calculations of flange stresses in operation are calculated as per C6.2.7 and verified against code allowables. The stresses are also represented as percentage of allowables. Hub thickness analysis is performed as per C6.2.4.4. The nozzle opening calculations constitute verifying the neck thickness, shell stress verification as per C5.1.4. MDMT calculations done based on Appendix MA2. The rated MDMT is calculated. Now let's take a quick look at EN 13445 code. EN codes are available from versions 2002 through 2016 issue 3 or 2016-9. The nominal stress is selected under Design Conditions tab. The four construction groups 1 through 4 relates to the Z values used in the calculations. One of the useful features of AutoPIPE vessel is the on-screen warnings and error messages once the calculations are completed. The 5 errors with their error codes are shown above. The errors are listed in details at the end of the report, and the blue hyperlinks help navigate to the appropriate section of the report to help investigate and resolve the issues. The internal pressure-related calculations for conical shell include evaluating required thickness for cone and adjacent cylinder as per 7.6.4 and 7.4.2. The required thicknesses at the large and small ends of the conical junction are determined as per 7.6.7 and 7.6.8 respectively. External pressure calculations performed as per 13445-3 section 8.6.3. The criteria for acceptance, which is the external design pressure, need to be less than the ratio of calculated lower bound collapse pressure PR to the allowable stress is checked. The applicability of the conical shell junction check criteria is verified. The nozzle opening calculations are performed as per 9.5. While discussing the EN code, let's discuss a little bit about flange design. AutoPIPE vessel offers the EN 13445 Annexure G method of flange design. This is a more advanced method and an alternate rule to traditional Taylor forge method and is available for optimized flange design based on EN 13445 Annexure G EN 1591-2001 method. This method uses much more advanced gasket behavior analysis than the traditional Taylor forge method, which often produces inaccurate hub stress values. This alternate EN method results in a more economical design and ensures leak tightness and includes thermal effects. The flange can also be attached to a conical section and considers nonlinear elastic behavior of gasket. It also considers influence of mounting cycles on the gasket. Now let's move on to the German AD Markblatter code. AutoPIPE vessel offers AD Markblatter code from versions 1990 through 09-2016. Here is an example of the hemispherical head calculations performed using AD Markblatter code. Thickness verification and MAWP calculations are done as per part B3. The conical shell internal pressure calculations include cone thickness verifications as per 8.1.2, subsequently using 8.1.1 to check the thickness of the large and small end junctions during operational and horizontal test conditions. The conical shell external pressure calculations consist of permanent elongation limit check as per 8.2.2 stability check using 8.2.3 by elastic buckling and plastic deformation analysis, and finally verification of max pressure. For the external pressure calculations, the usual large and small end conical junction area and inertia verifications are performed using 8.2.2 and 8.2.4. The conical shell internal pressure calculations consist of cone thickness verification as per 8.1.2 and inertia verifications as per 8.1.1. Let's review the British code PD 5500, which is available from versions 1997 through issue 04-2015. To the left is shown the conical shell under internal pressure. The thickness verification of cone and the junctions are performed as per 3.5.3. To the top right, cylindrical shell under internal pressure thickness verification per 3.5.1, and bottom right illustrates the nozzle opening thickness and reinforcement area verifications per table 3.5-4. Finally, also available are the Russian design codes GOST 52857 editions 1 and 2, 2012, and the Chinese GB 150, 2011. So far, the various pressure vessel design codes were reviewed and the calculation report samples were looked at. Let's move on to see some typical heat exchanger design code calculations. For our example, we would review the double fixed tube sheet or BEM type exchanger. Initially, the double fixed tube sheet exchanger was modeled without an expansion joint. As expected, there are several errors generated due to excessive stresses in tubes, tube-to-tube sheet joints, shell channel joint, etc. The Tubular Exchanger Manufacturers Association or TEMA standards are incorporated, and the above left image shows the report extract of the flow calculations and the shell or bundle entrance or exit area calculations. The right image shows the construction standard as TEMA under the bundle tab. A typical sample of the ASME UHX tube sheet calculations shown above in the above 3 screenshots of the calculations report. The design load conditions are specified at the beginning, followed by TEMA RCB 7.11 minimum thickness check, and then the detailed tube sheet design and stress verifications for the total 8 cases, 4 design and 4 operating. The final result of acceptance is clearly stated at the end. Each and every equation is clearly illustrated for easy reference. The expansion joint is a crucial part of heat exchanger design. The Bellows design can be performed based on Expansion Joint Manufacturers Association EJMA, ASME, CODAP, EN or AD codes. The flanged and fluid expansion joint analysis can be performed based on TEMA 8th method. In the latest version, the TEMA 9th method, which is based on axisymmetric finite elements, has been implemented as technology preview. However, in the first phase, only the stiffness calculation is offered. In the next release, the stress analysis of the joint shall also be implemented. There is also the choice of just specifying the spring rate in case a detailed analysis of expansion joint is not in the design scope of the user. This is sometimes the case, particularly in the event the joint is designed by a third party. Apart from ASME, just like our regular pressure components, the tube sheet calculations is offered in various design code options. In total, the tube sheet can be designed using one of the 7 code options, namely TEMA, CODAP, AD Merckbatter, PT5500, EN, ASME, and GOST. There is a supplementary design data section in the tube sheet design window. Some examples include specifying the diameter of untubed area for fixed tube sheet for AD code, options for U-tube exchanger in AD code for 6.7.3, design factors per table 1 of AD-B5 for stationary and floating tube sheet on the shell side and tube side, input for tube force calculations, several options for UHX special cases, and conditions and specifying FR and FE factors and interface pressures to calculate applied loads at the tube-to-tube sheet junctions for PD and ASME codes. In this third section of our webinar, we will review the design code options for wind and seismic loadings. The wind and seismic design codes include most major global codes including ASCE, AD, British, Indian IS, NBR, UBC, Spanish, Portuguese, Canadian NBC, GOST, IBC, Chinese, GB, Turkish. Also, user-defined values can be used for performing wind and seismic analysis. The wind and seismic variables can be specified from under the Load Conditions tab. The drop-down offers the available codes to select from. The report extract shows the calculation of the wind dynamic pressure QZ, the gust factors, and the equations for calculating the wind loads at each level, which yields finally the stresses at different levels. Likewise, the earthquake base shear calculations and the equations for calculating lateral seismic loads at various levels are shown. The moments and shear forces due to wind seismic loads are illustrated in the example figure to the right. Let's look at some material standards and local load methods now. Most widely used material standards are available in AutoPIPE vessels, specifically ASME, AD, ASTM, BS, DIN, EN, GB, GOST, and NFA. The local load analysis can be performed as per PD5500 Annexure G, WRC 107537, EN 13445, GOST method, and also Roark and Zig formulae. The WRC method uses the radial and 2 shear loads and the 2 bending and 1 torsional moments to calculate the total and membrane stresses as illustrated. The resulting stresses are evidently within limits. The previous modeling example was reanalyzed, now using EN 13445 local load method instead of WRC. Observe that only radial force Fz and circumferential and longitudinal bending moments Mx and My are considered in EN method. No shear loads and torsional moments are taken into consideration. In this final section of the webinar, let's look at some other types of equipment and find out what codes and standards can be designed those in accordance with. The air cooler modeling and analysis can be done using ASME code and API 661 standard. The extracts from the design report are shown to the right. The header design report as illustrated is performed in accordance with ASME and API 661, 6.1.6.16, and the bundle tube calculations as per ASME Appendix 1. The storage tank can be designed using API 650 11th and 12th editions, the last updated version being 12th edition March 2013. The report sample shows well size and load checks performed according to API 620 and API 650. The wind girder calculations performed as per ASC 7-5 and API 5.9.7.1. The support design in AutoPIPE vessel also uses various design standards. For example, for anchor design, the method used can be as per Thomson, A.D. Markblatter, Piles, GOST, CODAP, and EN 13445. For horizontal vessel support saddles, the methods available are BS PD 5500 plus ZIG, CODAP plus ZIG, EN 13445, ADS 3x2, ASME 8 Division 2, and GOST. In closing, I just want to draw your attention to a great resource for anyone wanting to learn more about the Bentley pipe stress products. Our YouTube channel has a variety of videos covering all aspects of our products, and more are being added each week. So if you're interested to see what's new or how to use a certain feature, subscribe and search the Bentley Pipe Stress Analysis channel. And if there is something you wish were covered but isn't, please drop us a line. We are always looking for ideas for additional content. The Select Connect edition was introduced in April 2017, and it is the most significant enhancement to Bentley's Select program since its inception. Select Connect Edition continues to provide comprehensive coverage for your Bentley perpetual licenses, but now offers every subscriber the option to also equip their teams through quarterly term licenses. Applications covered under Select can be pooled so that they can be shared, and you can exchange titles once a year through portfolio balancing to adjust to your changing project requirements. Most significantly, we are introducing Select CONNECTservices, new Azure-based services that deliver comprehensive learning, mobility, and collaboration benefits, now included with your Select subscription. So you can now take advantage of these CONNECTservices. Adaptive Learning Services access all Bentley learning content. Master use of Bentley applications through personalized in-application contextual learning. Personal mobility services, individuals working anytime from any place through Bentley's app. Project-wise connection services. Teams securely create, share, and deliver data and documents and review project status and performance. Go to connect.bentley.com today to get started. With this, I would like to end the webinar. Thanks for watching.